Welcome to the first of two screencasts that discuss the Gaussian distribution, sometimes known as the normal distribution. There are other names for it too, but Gaussian or normal, and I'll switch between these two names for it. Well, basically it looks like this. It's a nice symmetrical bell-shaped curve like that, with two axes. This one here is x, which is your random variable. So this could be height of a person, or weight of something, or an experimental error, anything that's uncertain. So uncertain variable goes along here. And here is the probability density. Which I won't go into too much detail, but basically it tells you where the most likely values of this uncertain variable are. So obviously you can see that it's centered around the center of this distribution, and the probability gets smaller and smaller as you go off to either side. It's a beautiful figure like that. Normally what you do is you make, if this is x here, you normally center it about x equals 0. And you can also control the width of this distribution as well, so you can make it a very narrow distribution like that, or a very wide distribution. So what you normally do is you consider what's called a standard Gaussian, which has got mean equals 0, and the width of this distribution is slightly more problematical, because I can't draw it very well, but you can tell that it goes off to infinity on either side. It doesn't actually, even though I've drawn it incorrectly, it doesn't actually touch the axis. So you just define a notional width. That's the width there, and we call the width equals the standard deviation, because it's how much your observations tend to deviate from the mean, which is 0 in this case. Obviously they can do more or less, but that's a representative amount. So what you normally do is you say x equals 0 is the mean value, and you talk about the standard deviation equals 1. So it's n, oops, let's do that again, n 0, 1. There's the mean, 0, and here is the standard deviation of 1. So what's going to be special about this screencast is I'm going to use the R computer language, and I've got the R computer language here. This is the workspace for R, and I can type things in the command line here. 2 + 5 is 7. So it's what you call a command line interface, and you just give it a question and it basically answers. But what I'm going to show you now is how to use rnorm. And this is a sort of two-part function. There's R for random and norm for normal. And then you give it a pair of brackets, and let's just give it a 1. And there we have a random number drawn from the Gaussian or drawn from the normal distribution, 0.9339. If I do the same process again, we get a different answer. Sometimes it's positive and sometimes it's negative. Just do it once more. Positive, negative, negative. What it's showing us is samples from, or random samples from, our standard Gaussian. And you can see that sometimes the value was above 0, sometimes below 0. And so we're sampling randomly. But mostly you're going to get observations that are in this region here that's quite close to the mean of 0. Sometimes they're going to be a bit further away, but not too far away. And that's the kind of thing I want to investigate. So I'm just going to go back to R, and I'll show you how it works. If I go rnorm, let's say 20, now what I can do is get 20 numbers, and you see this number in square brackets here, that says that this one here is the first, second, third, that's the fourth, all the way up to the 19th and the 20th. So we give it 20 here, and it gives us 20 values outwards. Well, it's a little bit difficult to try and understand how these numbers all fit together, just to look at them. So what we can do is just draw a histogram of rnorm 20, and it will create for us, I'll just bring that into view here, a nice histogram. And you'll notice that this histogram isn't a very well. It's not a bad histogram, but it's not very smooth. It's got these sort of sudden sort of jumps and changes. It doesn't look very symmetrical and nice, and that's because we've got a very small sample size of only 20. If I do it again, here's star norm 20. We get a new fresh sample of 20, and we can see it's looking lumpy and bumpy. It goes up and down and up and down and up and down. And we can do the process again and again and again. I can actually make it look a little bit nicer by going colour equals, let's say, grey. And there we can see what's going on a bit better. There it is. You see sort of a vague bell-shaped curve, but it looks pretty lumpy and bumpy and messy. So what I'm going to do, instead of 20, I'm going to have a larger number of samples. Let's say 200, and then I'll ramp it up. And we're still seeing uncertainties and lumps and bumps, but now we're beginning to see, emerging out of the gloom, we're seeing this bell-shaped curve here. Just do that once more. See, sometimes it's left skewed, sometimes it's right skewed, and so forth. What I'm going to do is add a whole bunch of zeros there. What have we got? Is that 2 million? That's 2 million observations. And now we can see, emerging out of the gloom, we can see this beautiful, beautiful Gaussian shape here that shows us that most of our observations are between +2, which is here, and -2, which is here. But occasionally you get excursions to be outside that range. We can talk about the mathematics of that later, but for the moment just notice how nice and symmetrical this curve is and how nicely set out it is, purely because we've got such a large number of observations here. Oh, that was 200,000, not 2 million. I can change that though. I think I was counting my zeros wrong. Put another 0, and that's 2 million. And we can see it's hardly made any difference because 200,000 was plenty of observations. Let's just go back to our picture of this distribution here. And what we're seeing here is a sort of histogram of our nice smooth Gaussian curve. Where is it? Here it is. I can plot random observations in a slightly different way. If I go rnorm 100, let's say, there's 100. If I just go plot rnorm 100, then we can see here our distribution. We can see there's the first, oh, that's the first one, second, third, fourth, fifth, and so forth, all the way up to the 100th distribution. Is it that one or this one? I can't quite tell. But here we see a very different picture of what's going on. So we can get a much clearer vision, or a different vision from the histogram. Just trying to open this. There we go. I'll do it again. 100. There we go. So we can see the range, although you don't get an idea of the density. Put some more zeros in there. Is that 100,000? That's 100,000. Suddenly we get a much clearer picture that says that very nearly all my probability is between plus and minus 2, but there's occasional excursions, bigger and smaller. If I want help on these systems in the R world, I can go !rnorm, and that'll fire up a help page here. And there's other functions documented here, but I'm just talking about this one right now. And we can see here that we can change the mean and the standard deviation at will. It's picking up 0 for the mean and 1 for the standard deviation by default. I'm not telling it anything else, but I can change those. If I go up here, let's go back to doing 100, and I can specify mean equals, let's say, 3. Well, suddenly now my values are clustered around 3 rather than 0, and you see we're going up to 5 because that's 2 above 3, and down to about 1. And I can control the standard deviation as well. Standard deviation equals, let's say, 10, and now the numbers, as well as being centered about 3, instead of going up and down by about 2, they're going up and down by about 20, because I've made the standard deviation 10 times 10 times 1, 10 times the standard value. I think it's very important to sample from random distributions just to get a feel for how they work. I think it's an important thing to do to try and understand randomness. Let's try that. There we go. Most of your distribution is, most of your probability is centered around the middle there, but there's excursions up and down, and that's my take-home message for this screencast. I'll talk about the distribution from a mathematical perspective in the second screencast, but for right now I'm going to stop there. Okay.